Welcome to Spatial Data Models Part 2. So we're going to go through a quick overview of the basic types, and then we'll talk about a couple of specialized types, and then topology, which is a methodology for reducing errors in drawing vectors, essentially. All right, so you'll remember from next week, probably vector data is represented with coordinates. And those coordinates or those vector features have attributes tied to them. So kind of a very simple geometric representation of real-world entities. Does anybody remember our discussion of discrete objects? And what is the opposite? I could have put a pear deck on this slide, I didn't think of it. What is a discrete object versus, say, a continuous feature?
Well, continuous features could be elevation, and discrete objects could be like a point, building, or river.
Great. Yeah, so discrete objects tend to be more containerized, more categorized, versus a continuous feature, which is, in reality, there's not a containerized distinction between different points in that feature. We tend to containerize them to represent them, which gets them a little bit closer to a discrete entity, but we're trying to represent a continuous object versus a truly discrete object, which is a self-contained, unique entity. So there's kind of some gray in the middle there, in my opinion. Right, so vectors describe discrete features. If you remember, there's three main types, which is points, lines, and polygons. And we're going to talk today about some of the things that make up those features. For example, on a line, you'll have nodes at either end and vertices in between. Similarly, with polygons, typically you'll have a node that starts the polygon and then vertices that finish it off, closing on the initial node. So starting with points, they typically use a single coordinate pair. Sometimes that coordinate will have an elevation attached, so it will actually be a coordinate trio, I guess. You'll have an X and Y horizontal position and a Z elevation. And then each of those points has attributes associated with it. So if you've gotten to look at any of the attribute data that come with some of our lab materials, you'll see there's information about the features. And for a points file, that is directly related to each point. Each point will appear in the attribute table, whether or not it has attribute information. For lines, you have these coordinate pairs or trios. You can also have three-dimensional lines in a series. And most GIS systems, definitely in Esri, but not all, those points are in a specific order. So you have a start and stop of line, which is something to keep in mind if you're doing any representation with like arrows at the end of your lines, or where a direction of travel might matter. Make sure you're digitizing in the consistent direction, it's helpful. And you can have attributes related to the entire line. So your line has a name, perhaps, or a category of some sort. But you can also tie attributes to those individual points depending on how your GIS system is structured. So in a simple Esri shapefile, your attributes are tied to the line, but it might get more complex in other systems. So again, you have the node to start off and the vertices along the way, and then a node to close the line. And then your third main vector feature or vector type is the polygon, used to represent areas. They're formed by connecting points with lines but their attributes are tied to the entire area itself. Some of the other elements in here we'll get to a little bit more in topology, but you can have polygons that are adjacent with other polygons. If you're analyzing coverage over an entire area, this is really important because when you have completely adjacent objects, you're not leaving out any slivers of land that you might have missed or overlapping pieces. That's really important when you start analyzing coverage areas and you don't want to double count or miss pieces. And again, the attributes for those are linked to the entire polygon typically. You don't typically see attributes tied to the points along those polygons. All right, so this is just a little factoid about how Esri creates shapefiles. Esri is the originator of the shapefile, but it's an open source file type now controlled by the Open Data Commission that we talked about last week. Forgive me, I've already forgotten the name. I've got other things on the brain today. But so essentially there's a couple of consistent methodologies used. Your shapefile can be described with just the outline, but shapefiles can also have holes in them. So a shapefile might have an internal ring or multiple internal rings describing the holes. So when they talk about the vertices being listed so that the polygon is on the right, it's fairly straightforward for polygon number 3, which is this little Pac-Man eating the other polygon. You guys, can you see my mouse? Do I have that set correctly?
Yes.
Yes, we can.
Okay, so for polygon number 3, you're describing in an order so that the interior of the polygon is on the right of your line. So I'm starting at number 1 to 2 to 3, and my polygon area is to the right. Similarly with the outer polygon of polygon 1, I'm going to start at point 1 and then go 9 to 8 to 7 to 6. So the polygon that I'm describing is to the right on the inside of this feature that I'm drawing. But now when you start talking about part 2 of polygon 1, which is this internal beast in here, polygon 1 is just this outer donut ring. So to describe this cutout area, we started at 15 and we went in a counterclockwise direction that puts the polygon we're describing on the right side of those points. That separates out polygon 2, which is the donut hole in the middle, and proceeds in the other direction. This is entirely Esri trivia. I can't think of any reason other than getting really deep into Esri coding and mechanics to know this, but I thought it was interesting. It does sometimes matter when you're trying to visualize line files with a direction. So it's conceivable that you might want to do something similar with a polygon, where your symbology changes depending on the order of your vertices. So interesting factoid to know, but we won't dwell on it. Hopefully you've seen a couple of shapefiles now. There've been a couple in your labs, though not a ton. You'll notice if you just grab the .shp file that looks like the shapefile and leave the rest behind, you will not have a shapefile because a shapefile is actually a collection of files. The primary important 3 being the shapefile, geometry, which is the .shp that's so visible, and then the index file and the database. So the database houses your attribute data, and the index file is what tells your computer how to find everything. So without all 3 of those, it's not going to work. You can leave your projection file behind and have a shapefile still work. It possibly won't draw in the correct place, especially if you're bringing in a shapefile that has a different projection into a project that you've set up in a second projection. They won't draw where you think they should, and you'll have to fix some things there. But if you have a projection file that comes along with it that has the same name, so it would be rivers.prg, then most GIS software, definitely Esri and QGIS, will recognize that PRG file and recognize the shapefiles projection when it comes in. And then you have some additional files that can go along and add other information to that shapefile. So it's really important to either use the catalog view, just hit that. This is how a shapefile will look in catalog, and if you're moving shapefiles around and you grab this city's shapefile, then catalog will move all of these files with it. But if you're just moving them manually yourself, you want to make sure you grab everything that goes with it. So the Esri shapefile, like I said, was developed, or sorry, the shapefile was developed by Esri. It's an old open source format now. It doesn't manage topology in itself. You have software that can manage topology, and we'll get into that a little bit more detailed later, but the shapefile itself can allow non-topological errors into your data. It's limited in the storage, so every shapefile can only store a single data type because of the way that they're constructed. So you can't have points, lines, and polygons all in one file, which is a little bit inconvenient, and one of the reasons that we like to use geodatabases these days. It doesn't inherently contain any topology information, so it doesn't tell you right off the bat what your area of your polygons are, but you can calculate that information using your software. But for advantages, it's one of the most portable formats around because it's been used by every GIS software developed since Esri started sharing that format. And it's a very portable, very quick, efficient file format. Because there's really not much to it. All right. Does anybody recognize this slide from last week? We talked about how rasters can be represented as vector information. And we talked a little bit about contours, but now we're going to talk about TINs. They technically are a vector data set because they're constructed of points and tied to attributes, but they're a little bit complex in that they have some continuous tendencies. And they're very similar to the ways that we represent continuous data. So the triangulated irregular network, or the TIN model, has also been around for a very long time. I'm not sure how that corresponds to shapefiles, but a very widely used model. And the way that it works is that you collect all of these point information, and if you have any familiarity with survey, you'll recognize the importance in a TIN model. Each of the survey data points is held true. So you're not going to generalize information that you know to be true. You'll generalize the information in between those points, which is every surveyor's ideal of what you would do with their data, because they've been there, they've measured it, they've done some sort of QC. We can accept that data. So it's very commonly used to represent terrain. It happens to be triangular, and we'll talk a little bit about how the rules of TINs relate to that triangular model. And you end up with this faceted looking format. So I have a Pear Deck question on this one. And the question is, why might you use a TIN? When you think of reasons to use a TIN. So the reason to choose a TIN over, say, a zillion points is to save space. A lot of continuous data models take a lot of space, but then also to preserve that accuracy of the individual points that we talked about. So you're retaining some individual characteristics while capturing the whole, which I think makes it a really neat and underappreciated data model. So this is the way that the TIN model works. You're drawing triangles and enclosing those triangles in a circle. So your goal or your rule is that every triangle must fit inside a circle that does not enclose any other circles within it. So for that reason, this larger circle is an unacceptable circle because it has this data point hanging out within it. So the next TIN facet that you would draw would be the one that would enclose this triangle right here in another circle, and then you would branch out from that one to this next circle. So essentially, you can't get too far ahead of yourself if you follow those rules. So that was a really quick way to summarize all of these words right here. You're looking for the smallest possible triangle, and you're following the Delaunay triangulation rules, which best capture the surveyed or known point information in this TIN model. And these are the parts of a TIN, the points that make it up, and the edges that connect the points, which result in the facets. So it can be a really neat looking data model and can really emphasize features like ridge lines or linear features within your data, or areas of really complex geometry because you'll see the dense point collection. So one of the advantages is that very large flat areas can be easily modeled. You don't have to represent what doesn't exist. So you have a limited number of data points in a large area, which saves storage space. And then, like I said, you can focus on areas of complex topology and collect more points in those areas and have them better represented. So you're not stuck on a fixed gridded spacing like the raster data set. So you have some of the advantages of generalization with retaining the advantage of specialized detail where you need it.